Bueno, comenzamos. Hoy tengo el placer de presentarles al doctor Harrod. Es una persona que el tiempo que le he conocido y descubrí que más allá de ser un investigador renombrado en su área, es una persona muy abierta y dispuesta a colaborar desinteresadamente en distintos proyectos. Por eso cuando decidimos invitarlo al Congreso, aceptó inmediatamente y hasta propuso dictar un mini curso adelantándose a nuestro pedido. Chris ha tenido una carrera con diferentes perspectivas como biólogo de peces, realizando trabajos para el gobierno y consultorías independientes para luego reinsertarse en la academia, donde se siente más cómodo y ha tenido un crecimiento sostenido y muy sólido. Esa carrera lo ha llevado a estudiar y trabajar en distintos lugares, desde su Reino Unido natal, Irlanda y varios países del Caribe, entre otros, e inclusive revalidar sus estudios en Chile, donde reside actualmente. Allí es profesor titular de Ecología de Peces y Ecología Acuática del Instituto de Ciencias Naturales von Humboldt de la Universidad de Antofagasta. Primariamente es un ecólogo de peces, pero como él se describe, tiene muy amplios intereses, pasando por genética y ecología evolutiva de poblaciones, conservación y funcionamiento de ecosistemas, tanto marinos como de agua dulce, y especialmente le interesa describir procesos crípticos en la llamada ecología de isótopos estables. Desde este punto de vista, los isótopos estables nos va a hablar hoy como una manera diferente de observar la biodiversidad. Chris.
Gracias. ¿Está bien? ¿Sí? Ok, mira, primera cosa, lo siento, necesito hablar en inglés. Ok, entiendo castellano, pero mi no es tan perfecto. Ok, ¿está bien? Super. Ok, entonces me voy a hablar. Okay, so today what I want to do is try and convince you that you people, everyone here is interested in conservation and biodiversity. What I want to convince you is that you can use this technique, stable isotopes, to understand sometimes quite hidden features of biodiversity. So, and I've gone the wrong direction. Yep, sorry. There we go, wrong button. So I'm from here. This is Antofagasta in Chile, just sort of up the coast and across a bit from here. Yeah, the reason why I'm in Chile is this lady. Yeah, I fell in love with a Latina, and now I have two little Latinos. Even though he's a cryptic Latino, but he's a Latino. Okay. Hang on. There we go. So the other reason I'm really happy to be in Chile is there's so much to do, so much research. So this is the north of Chile here. This is Antofagasta, the Mejillones Peninsula, and this is Peru here, Bolivia, and Argentina over here. There's many cool things to study, many things to do. The Altiplano, the Salares. We have the Rio Loa. It runs through the Atacama Desert, and it's full of trout, full of trucha. Pelagic fisheries, kelp forests. I'm going to talk today about pelagic fisheries and kelp forests, but first I'm going to talk a little bit about isotopes. First of all, sorry, there's my group. We have a small group, but a productive group. Claudio Quezada is the postdoc. Karina and Felipe, Elsa and Horacio are technicians and PhD students and master students. And yeah, we focus on fish and stable isotopes really. So what are these funny things called stable isotopes? So what they are, they're atoms of the same element, but they just differ in mass number. They have the same number of protons, but a different number of neutrons. So we have two stable isotopes of carbon, carbon-12, which is very common in the environment, and a rarer, heavier form, carbon-13, which has an extra neutron. It's just ever so slightly heavier. Tiny amount, but it's ever so slightly heavier. And the abundance of different isotopes within each element differs. We have a common, typically light isotope here. So 12C is about 98.9% of all the carbon in the universe is 12C. And about 1% is 13C. The same thing for nitrogen and the other isotopes. Sometimes we have 3 or 4 stable isotopes. But the thing is, each of these different isotopes gives us information that's useful to us as ecologists. Carbon can tell us about the source of primary production. Nitrogen tells us things about denitrification or trophic level of a consumer. oxygen and hydrogen can give us information on temperature, hydrology, location on a continental scale. Okay, so I'm talking about stable isotopes, not radioactive isotopes like carbon-14. These are stable, so that means they're conserved in a system. They stay in the system. And that's important. So, most of the elements in the periodic table have more than one stable isotope, but as ecologists we tend to focus on these guys, the HCNOS. So hydrogen, carbon, nitrogen, oxygen and sulfur. That's because they're really important, because they're the building blocks of life. As well as phosphorus. These things are found in all of the biosphere, the hydrosphere and the atmosphere. Phosphorus only has one stable isotope, so we can't actually use it in the same way. But the rest of them are there and we can use them as tools. Oh, I've gone a little bit too ahead, like I was warned. Yeah, there we go. So they're conserved within the system, they stay around. The heavy isotope becomes concentrated or fractionated because it's that little bit heavier. It tends to build up following a chemical or biochemical reaction. Things like photosynthesis, excretion, respiration, assimilation, nitrification. So all of these processes have kind of a predictable effect on stable isotope ratios. So we can use the stable isotope ratios to track those processes, which is a good thing as ecologists. So in terms of ecology, evolution, biodiversity, conservation, there's lots of things we can use with isotopes. They can tell us things about individual traits, population, ecosystem, and even global level stuff. So again, a useful tool for us to understand the world and to conserve the world. So for example, a key question that we ask all the time is, what does this animal eat? And we've got various different methods. We can have stomach contents, so we catch the animal, we may have to kill it to take its stomach, we can shake it and maybe it'll... and this is what we expect as an undergraduate when we start our project, is to work on stomach contents, but often it looks like this. Or the stomach's empty, or whatever. Yeah, good luck identifying this to, whatever. Yeah, this is nice, this is nasty. We can look at other things. We can look at feces, scats. I prefer not. We can do visual observations with binoculars. That's good if the species is on land, if it's a bird. But what happens if it's active at night, or if it swims underwater? We can use criticam. That's very expensive. And these methods are all biased in their own way, because we tend to get this retention of hard-bodied prey. Conchas of caracoles, or the carapace of a crab or something like that. They're retained in the stomach versus something like, maybe the animal could have been eating a medusa, but the medusa, because it's gelatinous, is lost from the gut very quickly, or is absorbed quickly. So, what happens if we're feeding on microscopic prey? Maybe the animal regurgitated. And the big problem is that it only tells us diet at that time. We say in English, like a snapshot. A photo. So we want something that can maybe assimilate over longer, be indicative of feeding patterns over longer times. So there's another way, an alternative way, is to become a chemist. Sounds a bit weird, but because if you think about it, the tissues of a consumer are synthesized from the things that it's eaten and then assimilated. So chemically, you are what you eat, because the new tissues are made up of a combination of old tissues and new materials from your diet. So chemically you are... that's another important thing, is that the chemical composition of food varies in different environments and according to different primary production sources of different primary producers, so like between kelp and phytoplankton. So chemically you are what you eat, but also where you eat. So unfortunately this poor guy's pretty much McDonald's, but I keep jumping. In science, if you start getting into the maths and stuff, we go Bayesian, and we've started to develop Bayesian mixing models, and they're very good because they include error at various stages. Errors in the sources of food, in the mixtures, so the consumers, but also in this thing fractionation, because the values are not exactly 1 for carbon and 3.4 for nitrogen. That's a promedio, so that's a mean. So there's always a distribution around it. So these methods, these Bayesian methods, allow us to include uncertainty. And they give us the outputs and credibility intervals, so we can be 95% sure, for instance, that this consumer is eating, whatever this source is. Oh, sorry, this group is feeding on Zostra, whatever it is. So they're quite powerful. We can calculate trophic position. If we know the nitrogen isotope value of our consumer, the baseline, and the trophic position of our baseline, and the trophic fractionation value, we can estimate trophic position, just using this very simple equation. Sometimes we don't use the phytoplankton because phytoplankton can change its value from day to day. So we might use a primary consumer, like a filter feeding bivalve that feeds on phytoplankton over time and kind of averages out the value of phytoplankton. And then that would be, lambda in that case would be 2, and we just run the model again, and off we go. And again, we've taken a Bayesian view. So this is my postdoc, Claudio Quezada, who's like a mathematical genius. Like, every lab needs a Claudio, basically. Really. He's good. He's annoyingly good at everything. Always happy, and he's pretty good looking as well, so it's annoying. But him and I have developed this, it's on CRAN. If you use R, you can download it. And to basically take the Bayesian approach to that calculating trophic position. Which is proved here. This is just 2 lakes in Finland, Kilpisjärvi and Inarjärvi, and we've got these robust estimates of trophic position for different species. And we can compare the maximum trophic position or food chain length between the 2 lakes because it's the highest trophic position. So it's a very, because it's Bayesian, it's kind of robust, and it's in R, so it's open source. Here we go. So another concept has come is this idea of the isotopic niche. This was started by a guy called Mrs. Stuart Berhot, who's kind of famous in the isotope world. And his idea is that if you look at the variation in isotope values within a group of consumers or even within a community, that gives you an idea of the isotopic niche. So you compare Lake A, B or C, or I can compare the ocean here with the ocean in Antofagasta. The more isotopic variation, the wider the niche. And Seth Newsom and colleagues published this at the same time. The idea that you convert the isotope data using mixing models and you go to what they call P-space, which is probability space or proportional space. And it allows you to really neatly take those isotope values, which are frankly, they're not nonsense, but they don't mean anything to anybody. And here we can say that this guy is 100% intertidal, is foraging 100% intertidally, this one 100% in freshwater. Well, this group here is feeding on a mixture of intertidal, terrestrial and freshwater. So it's been a big move. I'm not going to go into that too much because we don't have time. But here's an instance where we've done the same. These are with medusas from Irlanda del Norte. Big scatter. These are different species over different times. And we've just converted it into percentage benthic carbon, because what we were showing in this paper is that they don't just feed on phytoplankton, they feed on benthic resources as well. And the trophic position of a jellyfish can range hugely, of a medusa. They're not just doing one thing. Cheers. Okay, so just to conclude the first part, that's me trying to sell isotopes to you. So we've got this rapid, relatively inexpensive, it's like $8 to $10 per sample, assessment of consumer diet and habitat use. And it gives us valid information at the level of even global ecosystem, community, species, blah, blah, blah. So it's cool. Believe me. So now we're going to talk about some case studies, 2 case studies from northern Chile. So this is what I talk about, cryptic stuff, like stuff that we don't know. We think we know about a species or a system, and then using some isotopes, we kind of open a door that didn't exist before. It reveals information that's probably quite relevant in terms of conservation. So, yeah. Again, northern Chile, this is my house is here. Lots of upwelling, and along the coastal fringe, huge kelp forests like Bosques de Macrauga. Very, very impressive. And they support big fisheries. Oh, back. Okay. Okay, so this is work by Jessica Pizarro. She's a professor in Iquique, but she's a PhD student as well in the group. And she's working on these guys, the anchoveta. Yeah. Supports the biggest fishery in the world, the most productive fishery in the world. Go on. Yeah, please, press. Okay, that's bizarre. We're missing a figure. Basically, don't worry about it. It's the comparing the different eastern boundary currents. These very productive upwelling zones that we see in the Benguela, Canary Islands, California, and the Humboldt current. Well, the Peruvians call it the Peruvian current, the Chileans call it the Chilean current. I'm PC, so I call it the Humboldt current, or the Peruvian-Chilean current. But this is Antofagasta again. This is a chlorophyll A satellite image, and it's in red and green, so I apologise if you're colourblind. But this colour is very productive. And you can see this upwelling. This is most of the upwellings in the summer. It's really intense in the summer, but even in the winter we have upwelling all the time. So this is what's producing, helping. We get this nutrient-rich water comes up to the surface. There's lots and lots and lots of sun there. It's the most powerful UV radiation in the world, a little bit further inland. But it's really strong sun, lots of phytoplankton, lots of carbon fixation, lots of zooplankton, lots of pelagic fishes. And this supports the most productive fishery in the world, mostly for anchoveta, but for jorel and other species. Oh, bloody hell. Back, a bit more. Oh, you're giving it all away. Go on. Back. Oh, my lordy. No, I know. Okay, that's good. You just wait there. I'll try. Let me try. So, these upwelling systems are very, very productive. In terms of production in toneladas per km squared, more productive than the Antarctic or Arctic. Back one, please. Back. Go to the fish-based picture, please. That's ace. So, fish-base is the kind of international standard source of information about fish. And in it's got data on diet. And I remind you, this is probably the most important fish in the world in terms of fisheries. And there's very little data in there on the diet. There's hardly any studies of diet of anchoveta. And it suggests that the trophic position, they call it trophic level or trophic position, is like 2.1 through to there's one here where it says 3, but the averaging like 2.5. Doesn't have any data for adults. The fisheries for adults, no data in there for adults. And this is driven by Daniel Pawley and his colleagues. Okay, so what they've done is I don't know if you've read about this thing about fishing down the food web and all the controversies. It's very kind of controversial, but the idea is that over time fisheries have selected the upper trophic level fishes and we're taking them away and we're going down the food web. Many arguments against the idea, but the thing here is this is the values if you include anchovetas. And this is where anchovies really dominated in this period. It was a huge fishery. And they give anchoveta a value of 2.2. Okay, here in this is an ecopath model, anchovies level 2. Horse mackerel or the jorel is almost 4. Anchovies are 2. They feed on phytoplankton. That's what they get energy. That's the idea. And there's a problem, because when they did the diet studies, they counted what was in the stomach. And anchovies swim and they feed with their mouths open and they swim, and they just take everything. So the stomachs are full of diatoms. The diatoms are very small and there's lots of them. but there's not much carbon in them, not much energy. So this is Pepe Espinosa from Imape in Peru, and he did a very clever thing. This is the average of the diet. This is the green is again, unfortunately, it's green and red. This is phytoplankton, little phytoplankton, copepods, euphasids, and others. When you convert it to carbon values, the phytoplankton means nothing, contributes nothing. It's trivial. So these use of numerical techniques to calculate diet have biased everybody's view of what anchovetas are doing. What's their function in the ecosystem? Our entire understanding of that food web. People talk about it as a short food web because they've got a value of 2.2. Things eat them, and there's not much above that. But it looks like they might be wrong. Same guy, Pepe, did another. Can you go back one, please? So this is a paper that was in marine biology. I actually edited this paper because I kept it in because I really thought it was a good paper. Using stable isotopes, they suggested that the trophic position for anchoveta is about 3.4 or 3.7, not 2.2. So a huge difference. So we wanted to examine this in Chile. Can you press one? There we go. So this is Antofagasta down here. We sampled along the coast. I say we, Jessica sampled along the coast. From 1, 3, 5 and 10 nautical miles from the coast. She sampled fish, the prey, the putative prey, all the different prey items, chlorophyll A, phytoplankton, blah, 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 the whole lot. It was a huge amount of work. And we have anchoveta and jurel from the commercial catch, taken, I think, about here. So what did we do? We isotope them, carbon and nitrogen, and what we're going to do is we're just going to look at the individual data, and we're going to use two of these R-based models to talk about some characteristic features, these key features of trophic ecology. The mixing model to estimate diet, and trophic position model to estimate the actual trophic position. And we're going to use phytoplankton as our baseline. So, okay. There, again, carbon, nitrogen. The white triangles are anchoveta. The black triangles are jurel, another fish, the horse mackerel, and various different prey. Phytoplankton, copepods, euphasids, and zoea, so like the crab larvae. First thing to notice is that the anchoveta includes two groups with really different nitrogen values. So that's all from one net. So we just get them, and they're doing there's two groups doing two very different things in terms of their nitrogen. And they're about a trophic level apart. And the high trophic level ones are kind of sitting with the jurel. There's a few of them covered by the jurel. These other ones are a lot lower. But the obvious thing is they're not feeding. If they're feeding on phytoplankton, remember you are what you eat plus 1, plus 3.4, they'd be here. So, like Pepe was showing that, 2.2 is not the answer. It's not to do with length. It's not like that we have a big, the two different nitrogen values. It's not because we have a big group and a small group. This is the mass. We can see they're all of a similar mass, typical mass for the fishery. And there's no kind of correlation between mass and delta 15N. So there's something interesting going on. These are the results of the mixing model for all anchoveta, the high delta 15N group and the low delta 15N group. And all this is a proportion from 0 to 1 of the diet. So the high delta 15N anchoveta are largely, according to the model, feeding on anchoveta larvae. They're cannibals. The low delta 15N anchoveta, no copepods really, euphasids, but lots and lots of the zoa, the crab larvae. So two groups doing quite different things. We can estimate their trophic land. This is the low trophic level group, sorry, the low delta 15N group, the high delta 15N, and the jurel as well. And big differences, and these are statistically significantly different. So, and this is the 2.2 line that people suggest. So As far as I know, no one's ever described this difference between the kind of two groups of like two different feeding modes. The trophic position is a lot higher than that assumed by Daniel Pauly and others. What does this mean for like ecosystem-based models like ecopath? Because it suggests to me that ecopath is going in the wrong direction. What does it mean for this mean trophic level index used as an indicator? It's actually included as an indicator of biological diversity in the Convention on Biological Diversity. And more evidence that the upwelling food chain isn't short. So it's very productive, but there's another reason for it. Maybe it's that cannibalism that's helping it, I don't know, but that food chain is not short. So now I'm going to move from a species and pelagic thing into the coastal zone, into the kelp forest. And the question here is, what fuels the kelp forest fish assemblage in northern Chile? This is something we recently published in Ecology. We've seen this before. All this upwelling means we've got very productive fishery. But the amazing thing, when I first got to Chile, I expected people to eat anchoveta. Because if you go to Spain or Portugal, there's like old guys hanging around on the corner grilling. They got a little parrilla, they got some anchoveta, a bit of wine, chatting, beautiful. Nobody in Chile eats anchoveta, it's just not available. Or really in Peru either. They eat things that are associated with the kelp forest. Like the invertebrates, this is the famous loco from Chile, it's predatory gastropod, lapa, erizos. All these fishes, these rock fishes, such as the rollizo, cabrilla, and bilagai, that live in the kelp forest. And here's a pretty unfortunate one we've caught in a net, a congrio in the net. So this is, you can see the kelp here. It's very, very complex, very productive ecosystem. Lots and lots of problems at the moment of over-extraction of alga. It's like there's a guerra de las algas at the moment, because it's like people are making like $500 a day by illegally extracting the alga. So it's one of the reasons why we're interested in it in terms of conservation. Guania soil. Okay. So about these fish, the bilagai, the cabrilla, and the rollizo, there's lots and lots of studies on them, on their diet, using stomach contents. And that tell us that they live, we know they live in the kelp forest, and we know that they feed on benthic invertebrates that live in the forest. Yeah. So the assumption's always been is that they're fueled by the macroalga. Here's a typical view of one of our sites. It's the Atacama Desert, so it's pretty extreme. No natural vegetation in the terrestrial zone. But when you go underwater, there's lots and lots of vegetation, lots of kelp, epilithic algae and green algae here, and we go down to softer bottoms and we have a little bit less kelp, but lots and lots of filter feeders, lots of amphipods, crabs, the whole very complex and biodiverse system, and very productive. I'll give it one more go. Okay, yeah, there we go, excellent. So, as I'm sure you're aware, there's quite a lot of work done by Chilean marine biologists. They're world-renowned. They've got great habitats to work on. They've done a lot of work for like 30, 40 years, and they're pretty knowledgeable. And through that work, there's like a common story that all of these kelp forest systems are fueled or fed by kelp. There's the macroalga that provides the carbon, the energy that allows all that diversity. So for instance, this is a book by Farinha et al. And it says that marine communities are supported by many sources of organic matter, including benthic algae and phytoplankton. But as exemplified by many ecological studies, it is mainly the large algae that support Chilean rocky subtidal communities. Phytoplankton only plays a secondary role. And when I first went to Chile, I liked to swim, I liked to dive, and I was shocked by two things. The water is very cold. It's like 14 degrees, so like I was just in my swimming shorts and the other thing is the water's green. It's full of particulate matter. It's like, I learned to dive in the Caribbean in Grand Turk, where the water is super clear, and this was the biggest extreme opposite I've ever seen, because there's just full of, like, what I would guess looking at it is phytoplankton derived organic material. But the water is pretty green. So I kind of questioned this as I started to read this idea that it's all kelp. There must be something coming from the, it's okay. And when we get to these models using EcoPath and EcoSim, there's assumption that phytoplankton doesn't really play a role. It's detritus. It's macroalgae that's fueling this. And that's based on usually these are literature based. People just go to books and say, oh, this animal feeds on this, therefore push it in the model and let it run, let it balance. But there are various sources of energy and nutrients. There's the periphyton, the macroalga, the kelp, but also phytoplankton. As I showed you before, there's lots of phytoplankton. Lots and lots and lots of phytoplankton. And year round there's phytoplankton. So my question was it fueling the system? So there is a potential for pelagic benthic coupling. We have all this production of phytoplankton. Is that finding its way into the kelp forest? Is it subsidising growth to any degree? So this is the typical drawing. All these reef-associated fishes live in the kelp, and this is the idea that they're probably fueled mostly by kelp, by benthic sources, not the red, mostly by blue. But alternatively, I promise this is red, this is phytoplankton could be fueling them. So the question is, is there any kind of subsidy by pelagic derived materials to these benthic fishes that are feeding on benthic invertebrates living in the kelp forest? If there is, what's the relative contribution? And to be honest, I expected it to be like 15 or 20%. That was my kind of 15-20%, little. So what we can do is isotopically, we can distinguish between phytoplankton and benthic algae. Because of the relative difficulty to get carbon dioxide in the cell, we get different delta 13C values. So this is a meta-analysis by France back in the 90s, but it still stands where we, on average, phytoplankton is depleted in the heavy isotope. It's lighter than benthic algae. So we see this pattern wherever we look for it, basically. So, if you could please, cheers. So we went across the coast of northern Chile. So this is Arica, and the border of Peru, Iquique, Tocopilla, Antofagasta, Tal, and Coquimbo. So it's about 1,000 kilometers. So pretty representative of northern Chile. We collected about 15 fish, either by harpon or by going to the market or going to the fishermen who were catching the fish there, so we could be sure that the fish were from that place. We collected invertebrates from the intertidal and the subtidal as our baseline indicators. I'll explain that in a minute. And we did it in summer and winter of 2009, 2010. Okay. So why did we use invertebrates? Rather than collecting the macroalgae and the phytoplankton, we kind of use long-lived macroinvertebrates to produce our endpoints, our indicators. We use Perimitulus, a filter-feeding bivalve, and we use grazing gastropods, such as this is Echina littorina, and this is, you can't see them, but this is kelp that's been grazed down by Tegula. It's a gastropod, a big gastropod, and they feed on the kelp. The filter feeders feed on the phytoplankton. So if we've got their isotope values, we've got our two endpoints. And we can estimate where the fish will be relative to them. So, back one. Back, please. Yeah, excellent. Okay, so we have our sites from the south, Coquimbo, Tal, Antofagasta, Tocopilla, Iquique. And these data are the winter and the summer combined. And what we can see is that the filter feeders, let me just have a look, are always depleted relative to the gastropods. So this fits really well with that picture I showed you from the France paper, the difference between the phytoplankton and the benthic algae. So we get a similar pattern that we get this kind of These are our endpoints. This is the pelagic endpoint, this is the benthic endpoint, pelagic, benthic, in each of the sites. So where are the fish? Remember, you are what you eat in carbon, you are what you eat plus one, más o menos. So they're not feeding directly on these prey always, they may be feeding on something else that preys on it. So they should be, if they're feeding on benthic, the fish here should be about here, 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 and here. They're not, oh dearie me, losing all the drama. The fish are by the pelagic. Ooh. They shouldn't be there. They should be here. If all the books are right, all the papers are right, all the assumptions are right, the ecopath models are right, they should be fueled by kelp. It doesn't look like they are. So as an example, this is these are the invertebrate data. These are the pelagic invertebrates, the benthic invertebrates. The filled are summer, the open are winter, and the numbers of the different sites. So if they're benthic, the fish should sit here, where this arrow is. But it's going to do it. Come on, please. There they are. They're sitting right above this kind of pelagic carbon pathway. So they're not where we expect them to be. So they're living in the kelp forest, but it doesn't look like they're getting their energy from the kelp. So we can use mixing models, and we use the mixing model here, a different one called Pcia, and this is a proportion of either pelagic or benthic carbon and nitrogen in the fish at each of the sites. And we can see that always it's at least more than 50%, and on average, it's actually 90%, the median. So we've got strong evidence for a pelagic, what we call a pelagic subsidy. The fish live in the kelp forest, but the things they're eating, the detritivores, looks like they're feeding on pelagic-derived materials rather than kelp. And that kind of makes sense a little bit. So this is the assumed. We don't have this, we have this. Lots and lots of pelagic carbon and nitrogen, energy and nutrients coming in and subsidising the growth. And these are the most important fishes for the local inshore fishery. So, yeah, we've looked at this. Okay, thank you. So we've looked at this rocky macroalgal reef system, and the benthic-derived carbon and nitrogen is available. But most of the biomass going into the fish is from a pelagic origin. And our established assumptions, the dogma, is wrong. So a bit like with the anchoveta, what we know is not right. So we need to think about what's going on. We're not saying kelp isn't important, it's hugely important, because it's the habitat. It's this complex, structurally complex environment that, there's lots of places to hide, lots of places to hunt. It's very important. It shades things from it allows a refuge from temperature as well as predation. But it's essential habitat, but it's not providing, at least when we studied it, providing carbon and nitrogen. So, lots of questions. What are the management implications? Well, they're pretty good really, because it stops us thinking in compartments. Biologists are very good at saying, I work in the subtidal, or I work in pelagic systems, and you never meet. And that's so stupid. Because of course they're interlinked. So for me it's a nice way of showing that, you've got to think of the bigger picture. I don't like to use the word holistic, but it kind of fits here. You've got to think of, you can't just think of the coastal zone, you've got to think of things that are going on offshore as well, happening offshore. Questions are, is it found in other upwelling regions? California, Benguela, Canary Islands, and how does it vary over time with like El Nino, La Nina? So these are things we're studying over time. We're maintaining these studies. And the big question for me is how? What is the mechanism? How does that pelagic-derived material get into these benthic fish, but probably through benthic invertebrates? So we have a Fundación program on that at the moment. So to summarise, I hope I've convinced you or explained why isotope analysis should be a standard tool for ecologists, but also associated researchers, anthropologists, environmental scientists, behavioural ecologists, evolutionary ecologists. There was an early focus on food webs, but now we've got these isotope-derived matrix, which are really helping us understand the ecology of biodiversity. Here we've exposed two unknown features of two quite important fisheries or things that are supporting fisheries in northern Chile. And I always say to my students, how would you do that using another method? I'm an evangelist for isotopes. So, yeah. But I use lots of different methods. I use morphometrics, I use genetics, I use fatty acids, but I've not been able to show those patterns using another method. So, and I think it's a good way of demonstrating to other audiences what we've seen. So I'm just going to end with a little bit of advertising. We've successfully got funding to build a state-of-the-art, like the only one in Latin America, isotope facility in Antofagasta. And the whole idea is that we're collaborative. It's not to make sin lucro. The idea is that if you want to work on isotopes, if you want to have your students trained in isotopes, we'll run things at the cost price. So, already got collaborations with Mateus. Please, if you're students or if you want to come to Chile and to use this method, you're more than welcome, okay? And there's lots of things we can do, not just like, we can even do food stuff, geology, astrobiology. And to end, another advert, if this thing will let me, okay. Yeah, we're going to hold the biggest isotope ecology meeting in Chile next year in Viña del Mar, beautiful Viña del Mar, between July 30th and August the 3rd. So that's really it's like this conference, it's very friendly, okay? So you go there, you'll make friends for life, and the isotope grades go there, and it's brilliant. So if you're working on isotopes, you want to work on isotopes, please, there will be a website up and running soon, so you'll be more than welcome. So I'd like to end, go back, oh dearie me, oh well, no importa. It's just, there we go. So, yeah, there's one thing else I have to say. I have to thank all these people for funding. One great thing about Chile is they're pretty good at funding science. I have to thank the university, all the group. And if you want to contact me, if you've got a question about isotopes, you want to talk about potential projects, if you're a student and you want to come and do a practice or exactamente. Yeah, as in my lab, the lab always has at least one foreign student in at any one time. Okay, it's a very small lab, but we find space. And the one final thing is, if you're a student, early career research or whatever, use Twitter. Use it. You'll find jobs, positions, grants. Because I know in Argentina it's hard to get money, and there's people on there from every corner of the earth looking for partners. Okay? You've got great environments here, you've got great skills. If you use Twitter, you'll find lots of help. So I'd like to thank the organisers for the invitation to come. It's been great. I've found new friends and lots of new nice environments to work in. And yeah, obviously I'm very happy to answer any questions. Thank you. And thank you for waiting to the end. Cheers.